Hi everyone, it's me, Carolyn again, and we are going to finish up section 6.2 on the binomial distribution. Our last video was quite lengthy. I did go through quite a few examples on how to find some probabilities of a binomial, and also took you to StatCrunch and Excel to do most of the work for us. Technology is nice when you have one that works. Again, you can use the formulas on those. Feel free to do so. But I do think technology can save us some time. I do enjoy using StatCrunch for that because it does give us a picture of what's going on as well. In this video, like I said, we're going to finish up 6.2 because we have just a few more things to talk about. And this one, we will not really need any technology for it, but it does kind of pull some things together. So I do want to start by sharing my screen to our guided notes. And we are going to do this as kind of part 2. And I want to recall the binomial distribution. So some things to remember. The binomial had 4 criteria that had to happen before it was a binomial. We had to have a fixed number of trials. We had to, excuse me, had to have each of those trials was independent, so one did not affect the other. If we had 2 outcomes, or it could be boiled down to 2 outcomes, one we'd call a success, and the other one we'd usually call a failure. And the probability of a success did not change from trial to trial. Okay, in this video, what we're going to kind of look at is how do we find the mean or the average of these distributions. We did that in 6.1, and that was a weighted mean. We had to take x times our p of x and so forth. The nice thing is in a binomial, since we only have 2 outcomes, you know, a failure and a success, there is a short way to do this. And I'm just going to kind of think about an example. So you will almost probably try to answer the question yourself and come up with that formula, which I have on the screen, but probably should hide it. But let's say we have a survey and it says that 35% of people prefer color, the color purple, to any other color. And again, this is not a true statement. It's just one I made up. So, but let's just suppose that 35% of people prefer the color purple. Now, if you asked 500 people, how many could we expect to prefer purple? First of all, this is a binomial because we have 500 independent people. Again, I didn't write the words in there, but assume that we had a random sample of 500 people. So they would be independent. We have a fixed number of trials, 500, and so forth. So let's say you could think, well, that's just going to be 35% of our 500. And that's exactly what this is. It is true. So we can find our mean of a binomial by taking our n and multiplying it by our p. I could do the math for you to show you that it does work, that this formula does pop out. But I think by kind of looking at a percentage, 35% of the 500 is the same as taking our 500 times our p, which is 0.35. We'd get that same result. So there is how we find the mean. And I'll kind of just, so we get 175. So we would expect 175 of our 500 people to prefer purple. We also have the following, and again, I'm not going to go through the formula for this, is we can calculate the standard deviation. We don't have to add up a bunch of things and subtract a bunch of things and we have to square root. But it turns out that it's a lot nicer when we have this binomial to find our standard deviation. So for our example, we'll kind of go through our p's. Our standard deviation, notice I did not have the squared on there, so it's not the variance. Standard deviation is our sigma. We use the x to refer back to the binomial that we're looking at, or the random variable that we're looking at. Is going to be a square root of our 500 times our p times our 1 minus p. I'll clean this up a little bit before I go to the calculator. Namely, doing some of that subtraction in here first. Now, remembering the order of operations, I do have to multiply those pieces underneath, first of all. So under here, I have 113.75. Yes, you could have done it all in one line. That would have worked for you. But we get 10 point, I'll just go 665 if I round to 3 decimals. So a little bit easier to calculate. We also have some really nice things that also happen. If we have a binomial and we look at this n times p times 1 minus p, if that's bigger than or equal to 10, the distribution is going to be approximately bell-shaped. Okay, is that true for our example? Well, if I look at n times p times 1 minus p, that was the part that's right underneath here. So my 500 times my 0.35 times my 1 minus 0.35, which is 0.65, I got that 113.75. So my picture, if I were looking at StatCrunch, would be somewhat normal. You'd see that bell shape. And you'll notice that when we had some of them, they were bell-shaped. Some of them are a little bit bell-shaped on one side. But if your n gets big enough, your binomial will start to take on that bell-shaped curve. So here, for our example, it is going to be somewhat bell-shaped. And you're like thinking, so what? Well, the nice thing is kind of bringing some of these pieces together. If you can remember from the empirical rule, okay, the second part of the empirical rule, it said that 95% of our data, okay, if we had a bell shape, which if in a binomial n is big enough, we get that np 1 minus p, bigger than 10, here's our mean. If we went 2 standard deviations up and 2 standard deviations down, we would have roughly 95% of our data. Okay, what this tells us is that if you are outside, you are over here or over here, you're everything else. So these two pieces here is 5% or 0.05. Outside there is unusual. And a lot of times we want to make those unusual pieces. We want to know what's unusual, what's normal. And so for our example, we could find those unusual boundaries. So what we need to do is remember we're going to go from the mean up to standard deviations. And down to. Okay, so if I take my mean from the previous page, my mean was 175. That was at 500 times my 0.35. And my standard deviation was, I'm going to abbreviate here. We found it to be 10 points, and I'll just go 67, just rounding it to 2 decimals. My boundaries are going to be 175 plus 2 of these, and 175 minus 2 of those. So I'm going to drag out my calculator, do my multiplying first. So 2 times 10.67 was 21.34. If I add that on to 175, I'm going to write it down here for us, kind of avoid this area. I get 196.34. So if I am bigger than that, so if I came up and I said, hey, I've got 300, we were only doing 500 people, 300 people preferred purple. That would be unusual because it's more than this 196. If I went the other direction, 153.66 is if I subtracted. So if I told you that fewer than that 100 people thought purple was best, that would have been also unusual. Okay, an example of where you might see this. And I'm going to show you kind of some of the things we could do. Okay, let's say we're at a casino and someone is playing a game and they roll where they're rolling a regular die. And if they roll a 4, they win. All of the numbers are losers. Okay, and someone just told you that this person just rolled a 4, 47 out of the 100 rolls. Would this be unusual? We can do this a couple of ways. And well, we could find out what is that probability. Well, that would make us remember how to calculate that formula, or we'd have to have StatCrunch or something to do that. The first thing I'm going to check and see if my n times p times my 1 minus p, what that looks like. Okay, my n is my 100 rolls. It is a binomial because it's a regular die. Each roll is separate. We're only rolling it 100 times. So that's my n. My p is my 1/6. 1 minus 1/6. So 100 times 1/6 times 5/6, which is 13.8 something. How to say 89. Does repeat, which is bigger than 10. We can use that binomial kind of thing. The standard curve, we got a nice, beautiful bell shape. So we'll be able to do the second piece. Okay, which is what I'm getting set up for here. But here, we could have went in and said, okay, what's the probability that x is equal to 47? So we could have gone and done the calculations. N is equal to our 100. P is equal to 1/6, and my little x is 47. I could have done 100 C 47, going through back to my formula, times 1/6 to the 47th, 1 minus 1/6 to the 100 minus 47. And I could crank that out. And actually, I think I will. We could also go to StatCrunch. We could also go to Excel. I have my calculator handy here. Just won't take me too long. It might take me a while. It might take my calculator a while. Yeah, it's going to take my calculator a while. Times my 1/6. I'm raising that to the 47th power. That's a huge number. And I'm going to multiply that by 5/6 raised to the 53. Okay. I come up with 0.00, really small number. 3, 4, 5, 6, 7, 8, 9, 10, 11, 1, 4, 3. So this is, yes, unusual. Okay. If you think about it, a 4 should only happen. Your n times p, your mean, is your 100 times the 1/6. Your average would be about a 16.67, 2 decimals. Okay, that's our mean. So that's what we would expect to happen. We had it happen 47 times. But what we need to know is that unusual, well, we calculated it. Yes, our standard deviation, you'll notice, is that square root of n p 1 minus p. You'll notice we already calculated that n p 1 minus p up here. So that's that square root of 3.89. Was actually 88888. 13.89. And I come up with and I'll just go 73. Okay, so since I can use that empirical rule, if I go 16 and go 2 of these up, we would be roughly and we can get it in here 24.13. So any number above 24.13 would be unusual. Anything below about a 10 point something or 9 point something would also be unusual. So getting a 47 would spark some hints as to maybe we need to check out this die. Is this die loaded? That might be something. And doing this math compared to this math, a lot easier to do. Also starts bringing in some of the connections between that bell-shaped curve, which is a continuous thing being used to kind of approximate a discrete thing. Okay, I'm going to stop sharing here. This video was a little shorter than the last one because we had less examples. Calculating the mean and standard deviation of a binomial, a lot easier than calculating the mean and standard deviation of just a regular discrete random variable. So that's kind of nice. Our next unit, we'll look at one more probability distribution that again is used. There are others that are discrete probability distributions that are out there. We're just touching on a few. The binomial is probably one of the most used. There are a couple others. I'll mention the next one in the next video. And at that time, I'll also probably mention the third one that's kind of used at times. But until then, I will see you in the next video. And if you do have questions, please, by all means, email me.